I'm very happy to introduce you Shaun Quegan, who is the expert of the week on the topic of biosphere observations. Shaun is professor at the University of Sheffield in England, and he devotes a lot of his time to forests and biomass in general. Shaun, can you tell us a little bit about your background and what brought you into this very challenging field of research?
Well, my background is very strange, unusual, and it's very wide. My degree is in pure mathematics, so you might wonder how I ended up working in ecology or ecology-related fields. But my master's is in statistics, and my PhD is in ionospheric modelling, higher upper atmosphere modelling. And in between doing my master's and my PhD, I did 7 years teaching in schools, teaching children. And after that, I worked for Marconi. So I worked for Marconi for several years working on radar signal processing. And I moved to the University of Sheffield, and I carried on doing some of the processing work, the radar work, and the synthetic aperture radar in particular. But during that time, I became much more interested in applying this remote sensing technique to land applications. Now, again, I worked with the people over in Animal and Plant Sciences. We've got a very eminent department here in Animal and Plant Sciences. So I became interested in applying remote sensing to vegetation. Then I got the chance to establish what we call the Centre for Earth Observation Science in Sheffield. And this pulled together a large number of the elements in the university which were related to sensing of the Earth. So we had a hydrology part, an ocean, ice, and vegetation. And that was extremely successful. I directed it for 4 or 5 years. And every single strand of it developed into its own speciality and did very well. But I became particularly interested in working on the vegetation side, and then we were given Centre of Excellence status by the National Environmental Research Council of the UK in terrestrial carbon. So all the things which are related to the carbon cycle and the land, so the land atmosphere interactions to do with carbon. So I ran that for several years, and this was a combination between modelers, statisticians, engineers, ecologists. It's a whole bunch. It's a very multidisciplinary group of people. Then that became part of the National Centre for Earth Observation, which I ran the carbon cycle theme for that for several years, and now the National Centre for Earth Observation has developed in a slightly different way, but I'm still involved in that. So I ended up here with a very diverse range of skills, everything from hard mathematics through to experiment, through to statistics, through modeling, through signal processing, through knowing about radar. And so that's where I am here. And that's this range of skills that I bring to my current work, which is with biomass and forests.
So, related to the topic of this week, thinking of the biosphere, for me, trees and rainforests come into mind. Can you give us a little bit of an idea what your daily research includes?
There are really two major strands in what I do. One of them is work related to the European Space Agency biomass mission, which I think maybe we'll talk about later. And the other aspect is to do with modelling. And if you like, the core drive they're not separate. My core desire is to bring together observations and models to better understand the carbon cycle and get a better quantitative statement of how it works and how it will change over time. And so all the time I work with people who work on both models and data and uncertainty, because we want to know how well can we estimate the various things we deal. So, and it's not just in carbon. When you're dealing with land surface models, you have to worry about water. So water is a particularly important element of our models as well. In particular, you can't have a carbon model without also studying water.
So in the course we learn about satellite observations. So can satellites alone provide all the information we're looking for?
No. I mean, it's what you have to do is a very intelligent use of data, and not just satellite data, but in situ data with models. So what you're trying to do is constrain the calculations that you'd use to, say, do carbon flux, carbon emissions, or carbon uptake in biological systems and ecological systems. And you want to bring to bear on that problem the whole range of information you've got. Now, part of that is your biophysical understanding, and of course I have huge help from my colleagues over in Animal and Plant Sciences. They build the models that we use. But then the other side is to relate those models in some sensible way to the measurements you can make from a satellite or on the ground. Now, of course, there are very few things you can measure from a satellite that directly fit in those models. So you always have to worry about the translation between the two. So a major part of our intellectual effort is making the data talk to the models in a way that's coherent.
So I see that sounds like a very challenging and diversified job. But coming back to satellites, I know that you and your group are actively involved in a satellite project named Biomass. Can you tell us a little bit more about that?
Yes, the biomass, one of the big gaps in our knowledge of the Earth's biosphere is how much biomass there is in the Earth's forest and how it's changing. We also have uncertainties about other biomass in other sorts of vegetation, but biomass we can actually make some progress with on from satellite data. Now, the problem with measuring biomass from space is that if you're measuring the short wavelengths, or optical, for example, what you see are leaves. And leaves, they tell you a lot about the biochemistry, but the biomass is mainly concentrated in the trunks and the big branches of trees. So what you want to do is to have a system which can see through the green leafy part that we think of as a forest and see the things which are underneath. Now, to get down to those big parts where the biomass resides, you really need long wavelengths, and by that I mean radar wavelengths. Well, radar runs from about waves which are about 1 centimeter in length to, well, out into the meters. And from what I just said before, that if you're going to look for big things like trunks of trees in say, the tropical forest, you want to use a long wavelength because that will scatter off the big elements, because radiation likes to scatter off things about its own size. And so you want to use the longest wavelength you possibly can to get at the biomass element. Now, so in fact, if you really were doing it down with an aircraft, you should be using waves which are meter length. Unfortunately, from satellites, you've got to penetrate something called the ionosphere, which perturbs the waves very badly if you get to long wavelengths. And so the longest wavelength you can use in space is about 70 centimeters, which is what's called P-band. Now, up until 2004, that wavelength was not, you couldn't use it legally to look at the Earth. It was because the International Telecommunication Union, which controls frequency allocations, said that's reserved for what's called the space object tracking radars of the Department of Defense in the US. But in 2004, they made that wavelength available, that frequency available. And in 2005, together with Thuy Le Thuan from SBO in Toulouse in France, we put in a proposal, and the proposal was to build a satellite which would use this new opportunity and look at the biomass in the Earth's forest. So the fundamental concept is we asked for this long wavelength, but you need more than that. So the long wavelength on its own won't do it. You also need polarization. So you also need the ability to measure height from this, and to do that, you don't just want to see a forest once. You want to see it from two visits, which are closely spaced. So you can use something called interferometry to measure the height of the forest. And so the biomass mission is a single mission that will combine polarization, P-band, with polarization with interferometric capability that will allow us to measure both biomass and forest height across the world, across all the world's forests. It'll also give us this sort of quite high resolution, about 200 meters, which is unprecedented. And it'll give us to an accuracy of about 20%. You might think 20% isn't very good accuracy for if you're a physical scientist, but even on the ground in a tropical forest, you're not going to get accuracy from about 10 to 20%. So it's very comparable to what you'll measure on the ground. I should also add the biomass mission has a third technological aspect of it, which is what's called Readout Tomography. And that means that if you take multiple flight lines of the sensor, you can effectively create a layering. You can measure layers in the forest. So you don't just see so you can actually measure how much scattering there is in a series of layers down through the forest. So you can get information about how matter is distributed in the layer. And the biomass mission will therefore give us these three technologies: polarimetry, interferometry, and tomography, all of which give us information on biomass in forests.
So already you mentioned this resolution of 200 meter. That's amazing. So what kind of new insights are we expected to gain from such a high resolution observation or observations in general?
Well, first of all, there are no maps at this scale at all. In fact, up until about 2000 and I'm trying to think when I think the first maps have only come out in the last 3 or 4 years and there's a map produced at scales of kilometre or so for the boreal and temperate forests, and then there's other maps about 500 meters to a kilometre in the tropics. They use different technologies. So, but getting below those limits is very difficult at the sort of axes we're talking about. So we will get completely new information about how biomass is distributed. Also, we'll get biomass change because the mission is for 5 years, and this mission will be sensitive enough to see change in biomass, both loss of biomass and addition of biomass by growth of forests over the mission. So these are completely new sorts of information. I should also add that because we're looking at the Earth with a completely different wavelength, we've never seen it this way before because, as I said, it wasn't legal to look at the Earth at this P-band wavelength from space. This is the very first view we'll get at this wavelength. We will see things we don't expect. I'm certain of that. There's some things we're fairly sure we will be able to do, which is this will penetrate very, very deeply into places where that are arid. So to see subsurface prospecting for water, for example, it will be wonderful for that. We expect to be able to use it to measure scattering from ice sheets, for example, and tell us about structures of ice sheets. Hopefully velocity, there's a slight complication because of the ionosphere, which makes that difficult. It has potential for things like soil moisture, permafrost, and a range of other things. And also to produce a map of the surface, which effectively strips away the forest so you can see right at the, so in other words, what we call a bare earth topography of the planet. So there are some things we're fairly certain we'll get in addition to biomass and biomass change, and other things we've never thought of. We won't realize it until we actually see the data, which is this mission, as I should say, will launch in about 2020. So 4 years' time, 5 years' time, we will see the view of the Earth we've never seen before.
Thank you very much for sharing these promising insights with us. Can you say a few words to our participants who got interested now and want to study Earth science and eventually help with measuring the biosphere?
If you're entering this field now, you're entering at a golden age for observations. One of the events which has changed the way things will develop is the Europe's Copernicus program, which is putting into orbit a series of operational satellites. And so at the moment it's got this first two in what they call the Sentinel series to observe the Earth. Now, the operational is really important. It means that those observations will be there for the next 10 years or so. So you can think of building information systems, and you know you'll have the data. So it's worth putting in the effort to exploit these things to their full. For a one-off satellite, it can be a very big effort to develop an information system attached to it. So the Sentinel changes that game. There are also new developments in the in what are called these L-band radars. These are 24 centimeters radars, and they're becoming far more generally available. And they're very useful, for example, looking at tropical woodland, because this shorter wavelength is not good for high biomass forests in the tropics, but is good for regrowth and for woodland and for a lower biomass tropical forest and boreal forest, for example. So those are all new things. There are opportunities through the in 2018, we expect to get the Global Environmental Dynamics investigation on which is a LiDAR, space LiDAR, on the International Space Station, which again will give us amazing information about the vertical structure of forests, and we'll learn completely new things from that. And also combined with this is the fact that much of our knowledge of how to exploit these data is becoming mature. So we are in much more a position to know how to use these data intelligently to actually relate them to carbon calculations and to modeling. So this is the time when, if you want to have steady data streams that you can really use intelligently and together in a synergistic way with our understanding of how biospherical systems work, this is the time to start doing it. It's a golden age, as I said.
So you have heard it. You can help Shaun and his colleagues sensing planet Earth. Thank you, Shaun, for this very impressive interview.
Okay, thank you very much. All right. Bye, Thomas.